Hi, everyone. I've really enjoyed all of the talks and great discussions I've had this week. I'm excited to tell you about this work I spent a large portion of my pandemic on. There are a lot of pieces involved, so I'm mainly just going to try to motivate the approach that I've taken and share some interesting tidbits of physics. But there are lots and lots more details in this work I put up on the archive a few months ago. So the setting of the lithium problem is Big Bang Nucleosynthesis, so formation of light elements a few minutes after the hot Big Bang. And if you haven't thought very much about BBN before, it's really a remarkable theory. Once you have the standard model and nuclear physics, and once you've measured the CMB, then BBN is essentially a zero parameter theory. It's just a cross-check on how well we understand the universe. And it's a cross-check that takes place many orders of magnitude before recombination, which is where we really precisely understand what's going on. So how are we doing? I have some plots from this great review a couple of years ago. On the left, the theoretical prediction and observed abundance of helium-4 with 2 protons, which you can see we get great. On the right, this is the one that should really impress you, deuterium with 1 proton, even though it's down at the level of 1 part in 10 to the 5, we get it absolutely bang on. This is a great success of precision cosmology. But there is one more observable that with these characterizes our only semi-direct knowledge of the universe far before recombination, and that is the abundance of lithium with 3 protons. And in comparison to the other 2, here, we see far less lithium than has been predicted theoretically at enormous statistical significance. And this long-standing discrepancy is known as the lithium problem. Now, there have been particle physics investigations of BSM things in the past that aim toward this, but in my view, they all struggle because they don't do anything that specifically targets lithium. They want to do something like modifying the constants at the time of BBN or injecting some energy with just the right spectrum at just the right time. And unavoidably, that sort of ends up modifying everything a bit. And especially now that we've understood deuterium with such great precision, that's just not allowed anymore. So over lockdown, I set to think about whether there could be any sort of fundamental physics that could really specifically target lithium, which admittedly is sort of a crazy idea for a particle physicist to have. But to my surprise, I found this theory really remarkably close to the standard model in my opinion, and very much involved in or interconnected with the structure of the standard model. So that's where I'll actually start. I'm going to remind you of the discrete global symmetry enjoyed by the standard model fermions and ask whether they might also enjoy some discrete gauge symmetry. I'll write down just the simplest UV completion for that, the abelian Higgs, and then from this simple microphysical modification, there's going to be interesting phenomenology involving cosmic strings. And my story, my proposal at the end, is going to be that Big Bang nucleosynthesis proceeds as normal in the standard model prediction, but then later on, nuclei hit cosmic strings, and because of the symmetries, these cosmic strings can destroy 3 and only 3 protons and turn them into positrons at strong scale rates. So the cosmic strings then lower the lithium abundance from the prediction of the standard model amount down to the observed amount in the late universe. Okay, so I'm going to start with an important question about the real world that we don't talk about very much these days, which is that of proton stability. The theoretical bias that we have from grand unified theories discussed in the 80s is that the proton is always unstable. And that was great news because it meant we could build these enormous, fantastic detectors and look for proton decay as a signature of this very UV physics. But we've been very surprised over the last 40 years that rather than seeing proton decay, instead we've just gotten better and better limits on the lifetime of the proton. So in light of that, I think it's worth remembering that in the standard model itself, the proton is actually exactly stable. And the reason is because of a discrete symmetry, which is exactly respected by the standard model. This was actually mentioned yesterday by Juven. And so you'll recall when we write down the standard model of Lagrangian, we find these so-called accidental global symmetries of baryon and lepton number, rotations of quarks and leptons independently by an arbitrary amount. That's the symmetry of the Lagrangian. But then when we go to the quantum mechanical theory, these are partially broken by mixed anomalies with the standard model gauge group. And so what you get, what you'll find in all of the textbooks, is that it's just well, at least the continuous symmetry that's left over is just the linear combination of baryon minus lepton number, which is exactly conserved by the standard model. But that in itself wouldn't protect the proton. That still allows, for example, proton to positron decay. And indeed, that's what happens in grand unified theories. In fact, by virtue of the standard model having more than one generation, there's roughly another Z3 worth of anomaly-free discrete global symmetries. And that means that actually in the standard model, there is a Z6 subgroup of baryon plus lepton number, which is exactly conserved. The standard model can violate B plus L. We've heard about that all this week with sphalerons, but it only does so in units of 6. So proton decay, which would be a change in B plus L of 2, does not happen in the standard model. And so we've known about sphalerons forever. I think the importance of understanding the symmetry statement is that empirically, this symmetry seems to be very, 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 very good. So I think it's very well motivated to consider extensions to the standard model that respect the symmetry. And so I'm going to ensure that I do. So from the global symmetries now to the gauge symmetries and what unbroken gauge symmetries the standard model fermions enjoy. Of course, we know SU3 cross SU2 cross U1, but as we just saw, I just mentioned on the previous slide, baryon minus lepton number is also anomaly free. Once we know what the standard model fermions are, it has no mixed anomalies with the standard model gauge. And so it could be gauged without any additional charged matter under the standard model gauge group, which we haven't seen, of course. So then it's an empirical question as to whether or not there is some very weak additional force from some massless gauge boson. And thankfully, experimentalists have been doing these awesome, fantastic experiments, looking for fifth forces and being incredibly precise, and they haven't seen any. So if B minus L is ever gauged at any scale, it must be broken in the infrared. We don't see a massless boson. But good. So you might say that there's no B minus L, so now we've just landed back on the standard model. We know that's the infrared gauge group, but there could certainly be an unbroken discrete gauge subgroup of B minus L, which of course is also free of mixed anomalies, and doesn't come along with any of these pesky massless bosons that would mediate a fifth force. So to some extent, I think this is an ambiguity in what we know about the standard model fermions. And I think there really should be a program of trying to understand the signatures of a general ZN discrete subgroup of B minus L and how we could tell these apart. I'm not going to tell a general story today. I'm going to focus instead on a Z6 subgroup of B minus L motivated by keeping the proton stable. And good, thankfully, we've already heard some about discrete gauge theory today. So maybe you don't think it's as weird as the standard particle physics audience would. It's really very simple. You just, even though it sounds exotic, you just have an abelian Higgs theory where your Higgs field has a charge greater than 1. So in my case, I have a Higgs of charge 6 that's going to break B minus L. And because it has charge 6, it's not charged under a Z6 subgroup of B minus L. And so when it condenses and gets a VEV, it's going to completely break the continuous symmetry. The vector boson is going to get a mass, but this Z6 subgroup will persist into the infrared as legitimately an unbroken gauge symmetry. And now you might say, well, who cares? Some extra symmetry, but we don't have a massless boson. Indeed, there's no change to local physics. But having this extra discrete gauge symmetry means we're guaranteed to have cosmic strings. And I'm not going to belabor the cosmic string solutions, because we've heard lots already. But to distinguish them from the axion strings we've heard about, because this was a gauge U1, it means that these strings have a magnetic flux running through their cores. And importantly, as was already talked about by Ofri this morning, whenever you have a fundamental magnetic object, the magnetic charge is inversely proportional to the electric charge, which is very important. So we have these tubes of magnetic flux that might be out there floating around in the universe. That's an idealized solenoid. And so just like with your solenoid in the lab, there's going to be an analogue effect. You might have thought that required a massless photon. It doesn't. It's just for unbroken gauge symmetries. And when you take a B-L charge around one of these strings, it's going to pick up a phase, the charge times the magnetic flux. Because the magnetic flux is inversely proportional to the charge, the factors of the gauge coupling are going to cancel out. Good. And really, this is, well, good. So just to connect, Sung-Woo was talking a lot about the BF theory. This is also, the scenario I have is also a BF theory, and BF forms and things, very fancy language, but I think you can think of BF theory as just a generalized covariant theory of these discrete Aharonov-Bohm phases. Now, aside from dragging a charge around a loop, the cosmological scenario is of charges bouncing off cosmic strings. That's the scenario of interest. And you can actually do the calculation that was first done by Aharonov and Bohm in their original paper of just shooting a beam of particles at the cosmic string, well, the solenoid in their case. And you find that they have an enormous elastic cross-section, elastic scattering cross-section, which is entirely independent of any small couplings or large scales or small distances. And so is quite important for the phenomenology. Earlier, there was some questions about friction on cosmic strings. Indeed, for local cosmic strings, this causes a lot of friction in the early universe. Now, normally at this point, I'd say lots more things about cosmic strings that I'm going to, for the most part, skip because we've heard lots about them already. But there's one point I'd like to discuss in a bit of detail because I think it's interesting and it's important for my phenomenology, which is what happens when strings intersect. We have two cosmic strings I've tried to depict going in and out of the blackboard and zooming in on the place where they're going to intersect. And the question is, what is going to be the final state? Your intuition from free field theory is that most of the time, these things are just going to cross right through each other. Does that happen? Well, we can analyze this, in fact, by looking at slices of the 3 + 1 dimensional abelian Higgs and looking at the scattering of vortices in 2 + 1 dimensions. And in fact, I'm going to go to the supersymmetric limit, which to my knowledge is the only place where you can make a nice analytic argument, but numerically this behavior has been seen to apply far more generally. And supersymmetry is nice because then the collision can be analyzed in a moduli space. I'm just going to do the very simplest scenario, the n = 2 moduli space, where the only coordinate is just the displacement between the two vortices. So locally, we just have the plane. And then the question is, the plane I've tried to draw here, I want to consider a collision, a trajectory going toward the origin and ask what happens. And again, your intuition from free field theory would be that most of the time, these things just forward scatter and you go straight through. However, despite these vortices being large semi-classical objects, they're quantum mechanically indistinguishable. And so a displacement of r and of -r is physically the same situation, and we need to quotient our moduli space by this Z2 identification, which turns the plane into a cone, and it turns out a rounded off cone. And then this forward scattering corresponds to a scenario or a trajectory where you go up to the top of the cone and turn right around and come back. And intuitively, that's not what happens. In fact, you go up the cone and straight over this blue trajectory, which unfolds in real space back into 90-degree scattering. And so it's a fact that I was very surprised to learn that in the 2 + 1 dimensional abelian Higgs, vortices always scatter at right angles, always non-trivial. Now, how can we use this? Well, the important point going back to 3 + 1 dimensions is that we can look at different orthogonal slices of our configuration. For example, we can look at this green plane, and the two magnetic fluxes intersect this in the same direction. So on that plane, the interaction looks like vortex-vortex scattering in 2 + 1 dimensions, and you have to have this right angle scattering behavior. And in contrast, if I take a vertical slice, then the magnetic fluxes intersect this in opposite directions. So on this red slice, the interaction looks like vortex-anti-vortex annihilation. And afterwards, after the final state has to have no strings intersecting this red slice. So you might need to stare at this for a couple minutes to actually convince yourself. But indeed, it is the case that they never go straight through each other. They always have to intercommute or exchange partners. And this leads to really non-trivial dynamics of these cosmic strings. They cross each other and cut each other up, and in particular chop off closed loops, which as we've heard, can oscillate and emit gravitational waves and dissipate energy from the network. So rather than all of the cosmic strings diluting away or overclosing the universe, you have this really interesting non-trivial marginal behavior known as a scaling attractor solution, where in fact you always have a constant distribution of string lengths as a function of the Hubble distance, and in particular you have tons of strings at small scales. Okay, now I talked about earlier the Aharonov-Bohm effect and pointed out that there's this electric magnetic interplay that leads to this enormous elastic scattering cross-section. And it's a natural question as to whether there could be similar inelastic large scattering effects. And indeed, we heard about one just this morning. So the cosmic string case has seen relatively little study. So I'm going to remind you, or maybe rephrase some things that Ofri said this morning. With magnetic monopoles, you can find, as Ofri did, or really just from the Lorentz fourth law, that there's an additional component of the angular momentum that's stored in the electromagnetic field. It's the product of the electric and magnetic charges. It points from the monopole to the electron. And this immediately poses a severe puzzle, realized some 90 years ago, because you can imagine shooting an electron at a monopole. And again, your intuition from free field theory is that most of the time the electron should go straight through. But if that were to ever happen, then r hat, the displacement, will discontinuously flip, and that would violate angular momentum. So just as Ofri said, straight from the infrared, you can argue that the monopole must have non-trivial boundary conditions that pair up fermions of different chiralities so that that spin flip can make up for the change in angular momentum. And the Callan-Rubakov effect of monopoles catalyzing proton decay, thankfully we already learned what catalysis is that there is an enormous QCD scale cross-section for a proton to hit a monopole and turn into a positron. Again, entirely unsuppressed by UV scales or small couplings. Now, okay, of course, well, once you have learned from Tufte and Polyakov that the monopole is really a background configuration of your Higgs field, then you can understand it from the UV. I won't go into this. because the case of interest is really cosmic strings. And unfortunately, in contrast to the monopole case, there has been very little study of the cosmic string case. And in particular, I don't have, at least not yet, a nice infrared argument for why this very non-trivial scattering has to be there. But thankfully, there's this great paper by Alford, March Russell, and Wilczek from 1989, where they looked at cosmic strings of some U1 broken down to Zn, just like we have. And they had a leptoquark condensed on the core because they wanted to find the same sort of violation of B plus L that you get in grand unified theories for proton decay. And that allowed them to write down an effective interaction between the string core and a quark and lepton. And then they could do just an explicit quantum mechanical scattering calculation and find, again, an enormous scattering cross-section. And in particular, when your incoming quark has maximal discrete charge, because in a Zn group, the largest charge is n over 2. When the charge is maximized, again, the cross-section is entirely independent of any large symmetry breaking scalars or couplings. And you have, just like in the Callan-Rubakov effect, a unitarily limited cross-section for an incoming quark to turn into a lepton. Okay. Now, the case of interest for me is not exactly that, because I want to not break this symmetry that ensures proton stability in the standard model. So rather than having a leptoquark condense on the core, I'm going to have a scalar break the approximate global B plus L down to the same subgroup that the standard model exactly conserves. And I have to introduce some other scalars to communicate this breaking to the standard model fields. I can write down a Feynman diagram generating this effective interaction of lots of the standard model fermions with the string core. And it's at least approximately sensible to try to reshuffle all of those quarks into a fermion for the 3 protons and 1 for the 3 positrons, because the cosmological case of interest is indeed 3 protons being delivered to the string all together in the nuclear potential well of a lithium nucleus. So then I can approximately at least port over their results while ignoring lots of subtleties, and again find this enormous inelastic scattering cross-section for 3 protons to bounce off the cosmic string and turn into 3 positrons. And again, because we have 3 protons, baryon number of 3, and to Z6 gauge B minus L, the cross-section is entirely suppressed, a strong scale cross-section. Okay. Those are the ingredients. And then it's a numerical question as to whether or not this can actually be a large enough effect to destroy an order 1 fraction of lithium. And to the best of and what I can tell, the answer is yes. We had tons of cosmic strings from these really interesting non-trivial dynamics, and we have this enormous scattering cross-section. I want to emphasize there are tons of theoretical uncertainties. What I did on the previous slides really wasn't a calculation, and there are lots of uncertainties about how small cosmic strings behave, but I've chosen some benchmark that I think is reflective of what we think happens. And in that benchmark, you get an order 1 amount of lithium being destroyed for a B minus L breaking scale of something like 10 to the 8 GeV. But again, I don't want to claim any sort of precision on that. The point is just that this can plausibly happen at a large enough rate that lithium, most of the lithium could be destroyed by cosmic strings. To think about constraints, it's useful to unfold into, on the x-axis, the tension of the cosmic strings, on the y-axis, the time at which lithium is disintegrated. My benchmark is here in blue, but you can imagine trying to do this anywhere in this parameter space. We've heard a lot about the gravitational effects of cosmic strings, which indeed mean you can't go to very heavy cosmic strings. But in terms of when this happens, you don't really want to go past the CMB, but there's lots of time between Big Bang nucleosynthesis and recombination. And since lithium is only 1 part in 10 to the 10, and we have a mechanism that really just affects lithium, you can disintegrate lithium essentially however you want, and it's not going to affect anything that we've measured. Okay, so sorry I had to skate over lots and lots of details. for some conclusions, I think a very general point, which we should take away from both Sung-Woo's talk earlier and from this, is that cosmic strings can have really interesting non-gravitational interactions. And I think particle physicists have not paid attention to that, and they should. And in particular, for my money, these gauged B-L strings are especially well motivated, and it would be interesting to understand the case for general N and what are the constraints or signatures. As to the lithium problem in particular, I think this is a mechanism that you could actually believe in as a theorist. There's no incredibly fine-tuned parameters in order to only affect lithium. That comes out naturally. And I think I was incredibly surprised to find this so close to the standard model. Finally, to end on a somewhat lighthearted point, if you have a lead atom with 82 protons and it hits a cosmic string and 3 of the protons are turned into positrons, then you are left with a gold atom. So these cosmic strings literally perform alchemy. Right, thanks very much.